Hello students, today we start with the numericals on the chapter light. So we'll be doing each and every part of light numericals. In this video, we'll be specifically doing numericals of all the exercise of light chapter except for the lenses one. I will make a completely separate video for the lenses part. All the other parts will come in this video only. So starting with the first part of light, which you know is refraction at plane surfaces. And the first part basically deals with refractive index. I have gone through the chapter, you will be knowing about refractive index. The theory part I will not be explaining, will be coming to the formula and will be doing the numericals here. So we know that first of all we come through that refractive index part when we see the laws of refraction, where one of the laws says that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always constant, and that constant which is there we call it as refractive index. So based on that, if I just show you a refraction taking place, if this is a part separating the two parts over here, so if I am calling this as the first medium and second medium, and think this is the incident ray of light, I get the normal here, so you know that this is the angle of incidence. So this ray when going to the medium 2 will be bending. I am bending it currently towards the normal. So this is my refracted angle of refraction. So first of all, from the second law of refraction, we get the refractive index part coming. So first formula we will relate here is refractive index of medium 2 with respect to medium 1. It will be written like this. Try to get that how we write the refractive index part and how we read it. We write 1 mu 2, the symbol of refractive index is mu. It means the light ray is traveling from medium 1 to medium 2, but when we read it, we say refractive index of medium 2 with respect to medium 1. And in this case, going by that law, the formula comes as sin I by sin R. So this is the first formula which you get for refractive index. Now you know, you have studied that there is a bending of the light ray taking place while going from one medium to the other because the speed changes. And if the speed of light is changing, because of that the bending is taking place, it means refractive index of a medium should be depending upon the speed. And so based on that, we get a formula for refractive index of a medium based on the speed as this. Currently, I will be calling this as absolute refractive index. In absolute refractive index, the ray has to travel from air or vacuum. So in the numerator, when we find this refractive index formula, we have speed of light in air or vacuum. So whatever is the speed of light in air and vacuum, which you know, we take it as 3 into 10 to the power 8 meter per second, that will be written in that numerator part, and the second part will be the denominator part where it will be speed of light in the medium, whichever medium it is going to, the speed of light in that medium will be taking. So if I take a case that air is going, the light is going from air to any of the medium, so this one I will replace like this. So it means light ray is going from air to any medium. That medium could be glass, water, okay. So light ray is traveling from air to that medium. When we read it, it will be read as refractive index of the medium compared to the refractive index of air, okay, means refractive index of that medium compared to that air. So here we will get speed of light in air, which I will write it as CA, and then speed of light in that mediums. Remember, the speed of light will change. Okay, so that speed of light in that medium will be taken. We know that the speed of light in air is maximum. So that is there in the numerator. So the refractive index of any medium compared to air will never be less than 1, because numerator will always be greater than the denominator. Okay. So with speed, we have seen the formula for refractive index. I can change this with changing it, that air to any other medium. So if I write here G stands for glass, W stands for water. So the ray of light is traveling from glass to water. If I have to find the refractive index of this water with respect to glass on the basis of that speed, so it will be coming speed of light in glass divided by speed of light in water. Okay, so whichever medium is first, that medium speed will come in the numerator, followed by the medium which comes will be coming in the denominator part. Okay, so remember how we are taking which medium first, so that comes in the numerator. That will help you in remembering the formula. Okay, now again this we have written with respect to the speed of light. We can also write with respect to the absolute refractive index. So again for this one, if I want to write now refractive index of water with respect to glass in terms of absolute refractive index, okay, on deriving we get it as absolute refractive index of water by absolute refractive index of glass. So again I repeat, if I have to find the refractive index of water with respect to glass in terms of absolute refractive index, then absolute refractive index of water divided by the absolute refractive index of glass will come. I hope you are taking a note of how the formulas are there. In these, it was always first medium coming in the numerator part, but here first medium part comes in the denominator part. Then you know speed of light, because light is a electromagnetic wave. So the wave formula we know is V is equals to F lambda. So it depends upon the wavelength lambda also. So based on that wavelength, we can relate the speed formula also. So if I have to find the refractive index of water with respect to glass, and we are given the values of wavelength of a particular color of light in that medium, then the formula here, I will be replacing it here only, not writing separately. It will be wavelength of that particular color of light in glass divided by the wavelength of that particular color of light in water. So when wavelength is given, make use of this relationship to find the refractive index. Like here, it is of water with respect to glass. Okay. Then you will remember that the principle of reversibility of light also comes. Okay. According to that, you come to a derivation, and based on that, a very important formula relationship comes, which is of a great help while solving the numericals. So I will just do a partition here. Coming to the fifth one, that will be, if I have written like this, means I will read it as refractive index of medium 2 with respect to medium 1. This I will write it as 1 by 2 mu 1. It means refractive index of medium 1 with respect to medium 2. So if I know refractive index of a particular medium compared to another, but I want to reverse it, this way you can find it. Like I will give it with respect to two particular mediums. So if I take an example here, so I, for example, write here G mu W, it means refractive index of water with respect to glass. I need it over there, but I don't know have the value for this particular thing. but I have the value for refractive index of glass with respect to water. So if I just do the reciprocal of this, what I have, okay, and I can get the refractive index of water with respect to glass. So this will get written as 1 by W mu G. Remember, very important one to quickly get it. And all these, if you remember it, if it comes in MCQ, you can solve it mentally also. Now, we are seeing here the dependence of refractive index on speed of light and the wavelength of a particular color of light in that medium. So something very important to remember. With respect to the mediums, we name the mediums as rarer medium and denser medium. You know that the medium in which the speed is less, we call it as a denser medium, and rarer is the one in which the speed of light will be more. It is always a comparison. So let us write and remember certain things which I am telling here. If light rays are going from rarer to denser, so in this case, when a light ray is going from rarer to denser, remember mu will come greater than 1. Okay, so refractive index will be greater than 1, and happens to the wavelength, remember it will decrease. So wavelength will decrease. Okay, so this is the case when going from rarer to denser. So if I take it now the reverse one, denser to rarer, you know now refractive index will be less than 1, okay, and wavelength now in the earlier case it decreased, so it will increase. Okay, so there are two conditions. To avoid confusion, I always tell whenever two of them are there, to avoid confusion, always remember one of them and tell yourself the other one can be reversed. So these all will be used while doing the numericals of this first part, that is we will come to exercise 4A. So kindly note down all the formulas which have been written. Theory part, read it properly, understand, then coming to the numerical always helps. And writing all the formulas and then beginning it is of great help. The sums can be done easily. So let us see, we will move on to the numericals now. So we begin with the numericals of exercise 4A. There are only 4 numericals, so we will see one by one all of them. The first one, the speed of light in air is 3 into 10 to the power 8 meter per second. Calculate the speed of light in glass. The refractive index of glass is 1.5. So if it is told refractive index of glass, it means it is absolute refractive index, means the light is coming from air to glass. So we will make use of the speed of refractive index formula involving the speed of light. So we will write refractive index of glass with respect to air, A mu G. So that will be speed of light in air by speed of light in glass. So we are given refractive index as 1.5. So written 1.5. Speed of light in air is 3 into 10 to the power 8. And speed of light in glass we have to find. So we write Cg is equals to 3 into 10 to the power 8 by 1.5. So 3 divided by 1.5 will give us 2. So 2 into 10 to the power 8 meter per second is the speed of light in glass. So this is our answer, and it finishes a very simple and a short numerical. Now coming to numerical number 2, again a very simple and a short numerical. The speed of light in diamond is given as 125,000 kilometer per second. Okay. What is its refractive index? The speed of light in air is 3 into 10 to the power 8 meter per second. So speed is given. So to find the refractive index, this refractive index formula based on the speed will be used. So I will be writing here A for air and for diamond D. So refractive index of diamond with respect to air. So I will get here speed of light in air by speed of light in diamond. So writing that formula, refractive index of diamond with respect to air, speed of light in air by speed of light in diamond, and now we substitute the value. Speed of light in air is 3 into 10 to the power 8 meter per second, and in diamond it is 125,000 kilometer per second. So 125,000, it is in kilometers, so I should change to meter by multiplying with 1,000. So you can see altogether there are 3 and 3 6 zeros here and 8 zeros here. So we simplify it out, 6 zeros will get cancelled. I will get here 3 into 100 will be left, 2 zeros, and here these are cancelled, so I will be left with only 125. Now 25 fours are, 25 fives are, so I get 12 by 5. So if I divide 12 with 5, you know you will get it as 2.4. So refractive index of diamond with respect to air is 2.4. No unit, because refractive index is a ratio with the same quantities in numerator denominator, unit gets cancelled. So this is your answer. So now let us see numerical number 3. The refractive index of water with respect to air is 4 by 3. So refractive index of water with respect to air means the value of A mu W is given to you. What is the refractive index of air with respect to water? Now it is the reverse. Air with respect to water, you have to find, it means it is W mu A. So the relationship which we had seen based on the principle of reversibility of light, that will be followed here. Okay. So I have been given the value here of A mu W as 4 by 3. And we have to find the value for W mu A, it means refractive index of air with respect to water. So I will write here W mu A equals to 1 by A mu W. So 1 by 4 by 3 is given here. So this 3 will go up, divided by 4. So if you go to divide 3 with 4, you will get it as 0.75. So 0.75 is the refractive index of air with respect to water. So this sum is done. So let us see the last numerical of this part, which is based on wavelength and refractive index. Follow the question. A ray of light of wavelength 6600 angstrom suffer refraction from air to glass. So light is going from air to glass. Taking refractive index of glass with respect to air as 3 by 2, find the wavelength of light in glass. So you know, going from one medium to the other, the wavelength will change. So what is the wavelength of that light in glass? So we will be using this refractive index formula based on wavelength. So number 4. So I will write here A mu G. So light is going from air to glass with the wavelength formula, wavelength in air by wavelength in glass. Refractive index is given to us as 3 by 2. Wavelength in air is 6600 angstrom. So writing wavelength in glass. So wavelength in glass will come here. So 6600 into 2 by 3. 3 will cancel it here. 2200. So you get 4400 angstrom as the wavelength of that light in glass. So the last sum for this part was a very easy one, but you should remember the formula of refractive index based on wavelength also. So we'll move to the next part. Okay. So we'll see first the formulas involved over there, and then we will look into the numericals. Now let us take a look at the second part of this light chapter, which is based on refraction of light through a prism. So before coming to the numerical, this ray diagram based on prism and the different parts needs to be understood. ABC is a prism with angle of the prism as A, that will be used. So it's important to know. This is the incident ray striking the surface AB. Angle of incidence is I1. So it is going from rarer to denser medium. It is bending towards the normal. So when it bends here, this is R1 is the angle of refraction at the first medium, and because the ray has got bended, the first deviation takes place here, which is written as delta 1. Then it goes and strike the second medium, second surface AC, and it is coming out from glass to air, that is from denser to rarer. So this ray of light is moving away from the normal. The angle made between the normal and the incident ray at this surface is R2. Okay, that is the angle of incidence at the second surface, that is AC. And I2 is the angle of emergence. Delta 2 is the deviation taking place at this surface. This was our original incident ray, and the final emergent ray is this one. So when they are produced backward, you get an angle here which is called as angle of deviation, denoted by delta. So very important part is here this angle of deviation, because based on this angular deviation, angle of prism, angle of incidence and angle of emergence, all the relationship will be there. You have a derivation given in your textbook. We don't have to do those derivation. We will focus on the formula so we can apply them and do the numericals. So first relationship, where it is a connection between the angle of deviation, angle of incidence, angle of refraction at both the surfaces. So the first formula here is for angle of deviation. So delta is our angle of deviation. Remember that. The formula comes as I1 plus I2 minus R1 plus R2. So take a look properly in the diagram, and I1 is the angle of incidence, I2 is the angle of emergence, R1 is the angle of refraction in the first surface, R2 is the angle of incidence at the second surface. So this one is the first relationship. Then these two, R1 and R2, can be related with the angle of the prism. With this formula, angle of the prism will come as R1 plus R2. So if the two angles R1 and R2 are given, you can use this to get the angle of the prism. Then the third relationship, which is a very important one, which will get used while doing the numericals, connects between the I1 and I2, angle of incidence and emergence, angle of prism and angle of deviation. So it is I1 plus I2 is equal to the angle of prism plus the angle of deviation. So this is the one which will be used mostly. Then in this part you also have come across how does the angle of deviation depends upon the various factors, and one of those factors tells us is about the angle of incidence. If you take a certain angle of incidence and from there you start increasing the angle of incidence, what you will notice in the angle of deviation is that the angle of deviation begins to decrease. And then at a certain point, coming to that minimum angle, after that, if you still increase the angle of incidence, angle of deviation begins to increase then. So first it is showing an inverse relationship and then a direct relationship. So that minimum angle which we come to is called as angle of minimum deviation. And that angle of minimum deviation, when that happens, if this prism is equilateral prism or isosceles prism, two important things takes place, and remember that. In that case, I1 and I2 will be equal. So angle of incidence and emergence will be equal. And the second thing is that the refracted ray inside the prism will become parallel to the base of the prism. So remember these two very important part, and based on that angle of incidence and angle of refraction emergence are equal, this formula gets changed to, now it is a condition of minimum deviation. So we get here, remember this is delta min, means it is angle of minimum deviation. So it will be 2i. Why 2i? Because these two are equal. So I and I will get added to 2I minus the angle of the prism. So this is a very important formula to be remembered. When you have to find the angle of minimum deviation, it will be twice of the angle of incidence, or if the angle of emergence is given, and minus the angle of the prism. These formulas noted down, we will require them to do the numericals. We have very few numericals here. Let us take a look at them. Let us begin with the numerical of this exercise 4b, which has got only two numericals, and both of them are based on that same formula of angle of minimum deviation. Let us begin with the first one. The question says a ray of light incident at an angle of incidence of 48 degrees. So that is your angle of incidence given on a prism of refracting angle 60 degree. So 60 degree is the angle of the prism, that is A, suffers minimum deviation. So they have clearly told it is a minimum deviation condition. So you have to make use of the minimum deviation formula. Calculate the angle of minimum deviation. So we write that formula. So delta minimum is 2I minus A. So we have to find this only. So 2 into angle of incidence is 48 degree minus the angle of the prism 60. So 96 minus 60 degree gives you 36 degree. So this is the angle of minimum deviation, a very direct sums. Okay, now let us come to numerical number 2. What should be the angle of incidence? So now it has been asked, what is the angle of incidence for a ray of light which suffers a minimum deviation of 36 degree through an equilateral prism? So that equilateral prism makes the angle of prism as 60 degree. So let us write the formula first. So here the angle of minimum deviation is given as 36 degree. Angle of incidence we have to find, and because equilateral prism, so we write here angle of prism as 60 degree. So 36 plus 60 is equals to 2I. So I equals to 96 by 2 equals to 48 degree. That gives you the angle of incidence. Looking at the result, you must have made it out that they were just the same values, only the quantity to be found out were different. We come to the end of the numericals here of this part. We will move to the next part now. So now we move to the C part of this light topic, where you will be seeing that when rays are traveling from denser to rarer medium, you know it bends away from the normal. And when it bends away from the normal, the object is not visible at its actual place, but it looks raised up. So based on that only, we will be seeing first the formulas and then go to do few numericals which are given on it. So first of all, understand from this diagram what it is all about. This is a line separating the two medium, that is air and water. So here water is a denser medium, air is a rarer medium. In place of water, we could have had glass also. Now this is the position of the object. So O is the object and it is being seen from this point. So the rays are traveling from the object. When it comes to the separation of the medium, it is going from denser to rarer, so it bends away from the normal. So this ray, when reaches the person I, it seems that it is not coming from O, but it is coming from I. So this is the apparent position of that object. So the distance from O to A is called as the real depth, and the distance from I to A is called as the apparent depth. How much will be the apparent depth depends upon the refractive index of this medium with respect to air. In this case, it is water. So if the refractive index changes, this apparent depth will also change. And this length from O to I is the shift taking place. So what is the shift of that object to the position which it comes to? So we will have relationship based on refractive index, real depth, apparent depth and the shift. So let us see them one by one. So first of all, how is the refractive index deciding upon the apparent depth? So you have the first one where refractive index of the medium with respect to air, that medium in this case is water, but I will be taking it as medium only, will be depending upon the real depth and the apparent depth. So the refractive index here is the real depth divided by the apparent depth. So what is the real depth here? OA. So I can write this as OA and the apparent depth is here IA. So this is the first relationship which you need to remember, that the refractive index of the medium with respect to that air or the denser medium is the real depth by the apparent depth. Okay. Now from here we can relate how is that apparent depth related with this refractive index. So apparent depth will be equal to, refractive index comes here, apparent depth goes here. So it is real depth by the refractive index of the medium with respect to air. So you can see it is coming in the denominator. It means apparent depth will be inversely proportional to the refractive index of the medium. What does it mean? As the refractive index is going to increase, the apparent depth will decrease. Apparent depth decreasing means the position of I will be going up. So if I keep on making the denser medium with a higher refractive index, then I will be going up. So you will be getting a smaller apparent depth. So it means the object will be seen to be visible at a much higher height compared to its actual position. Now we will come to, because this shift part is depending upon the apparent depth as well as depending upon the refractive index. So we will get this shift, which I will first write it as, it is the real depth minus the apparent depth. Okay, so it is real depth minus the apparent depth. Real depth you know is OA. So we can write as OA minus IA also. Okay, so now if you are knowing the real depth and the apparent depth, real depth if it is given, apparent depth is calculated here, you can subtract both of them and get the shift. Even we can get a direct relationship for the shift as using the same thing, putting the value of apparent depth and then finding it. So it comes to real depth in the bracket 1 minus 1 by refractive index of the medium with respect to air. So if you are given the real depth and refractive index, you can put it here directly and find it out, or you can first find the apparent depth and subtract both of them and get it. Now a very important thing to relate. See, already I have told that the apparent depth is inversely proportional to the refractive index. It means if the refractive index increases, apparent depth decreases. So what happens to the shift? So see, if this is going to decrease, it means shift is going to increase. So if the refractive index is increasing, the shift will also increase. So in the numerical, you have to be clear whether it is the shift or the apparent depth is told and calculate accordingly. So again I repeat, apparent depth is inversely proportional to the refractive index, but the shift which is there is directly proportional to the refractive index. Now we will proceed to work out the few numericals which are there on this topic. So let us now come to the first numerical of this exercise 4C. The question goes like this: a water pond appears to be 3 meters deep. That means appears to be, so that is the apparent depth. If the refractive index of water is 4 by 3, so refractive index of water given means it is with respect to air, so that is 4 by 3. Find the actual depth of the pond. It means you have to find the real depth of that pond over there. So first of all, we put this value, 3 meter is the apparent depth. That is 3 meter. Then the refractive index here, that is the medium is water, I am still writing as medium, is 4 by 3. So you know the formula that the refractive index of the medium is real depth divided by the apparent depth. So now let us substitute the values. So 4 by 3, real depth we have to find, and the apparent depth is given to us 3. So we can write here real depth is equals to 4 by 3 into 3. So reducing, we get the real depth of the pond to be as 4 meter. So if the formula is known, it is directly writing the formula, substituting the value and solving it. So now let us take a look at the second numerical, which goes like this. A coin is placed at the bottom of a beaker containing water. Refractive index is given as 4 by 3 at a depth of 16 centimeters. So the coin is placed at a depth of 16 centimeters. So that becomes the real depth. By what height the coin appears to be raised when seen from vertically above. At what height the coin appears to be raised means by how much it is raised. So that is the shift being asked. If it was told at what height it is visible, then it would have been apparent depth. So you have to carefully understand the question, which case they are asking apparent depth and which case it is the shift. So we know the real depth, we know the refractive index. Let us first calculate the apparent depth. Okay, so I go with the formula first. So I have written in short real depth as R dot D and apparent depth as A dot D. So I know the refractive index here as 4 by 3. Real depth as 16 and apparent depth I don't know. So I will calculate that first. So I get apparent depth equals to 16 into 3 by 4. That will get cancelled. And 4 4s are, so I get it as 12 centimeter. So I know the apparent depth as 12 centimeter and I know the real depth as 16 centimeter. So I can now find the shift as real depth minus apparent depth. So that is 16 minus 12 equals to 4 centimeter. So here I went with the procedure of finding the apparent depth and subtracting the two to get the shift. But I can do it in the other way also, where we know the direct formula of shift. So another way of working out the same sum, shift is equal to, you know, it is real depth in the bracket 1 minus 1 by refractive index of the medium. So this is 16, 1 minus refractive index is 4 by 3, it is there in the denominator. So 1 by 4, that by 3 will come to the numerator. So you get 16 into, so LCM will come as 4, 4 minus 3 will give you 1, and so now reducing it, you will get that shift as 4 centimeter. You can use any of the method which you find it convenient. So let us come to the third and the last numerical of this part. Question is like this: a postage stamp kept below a rectangular glass slab. So there's a postage stamp and a glass slab has been put over it. It has a refractive index of 1.5. So the refractive index of the medium is given to us. When viewed vertically above it, it appears to be raised by 7 millimeter. appears to be raised by 7 millimeter, means the shift is 7 millimeter. Calculate the thickness of the glass slab. So see, thickness of the glass slab becomes the real depth. So you have to find the real depth. Apparent depth is given, and not apparent depth is given, shift is given, and we have to calculate the thickness of the glass slab, that is the real depth. So I will be making use of the shift formula. So shift is real depth 1 minus 1 by the refractive index of the medium. Here the refractive index is of the glass slab. So the shift is given to me as 7 millimeter. Real depth we have to calculate 1 minus 1 by refractive index is given as 1.5. So 7 real depth copied. So this will be 1.5. 1.5 into 1 is 1.5 minus 1. So this will give me 0.5 by 1.5. You know, decimal removed, it is 5 by 15. So I cancel it to write here 3. So this will go and multiply here. So real depth becomes 3 into 7 as 21 millimeter. If I convert it to centimeter divided by 10, so I get it as 2.1 centimeter. This is the thickness of the glass slab, which is the real depth. So thickness of the glass slab is equal to 2.1 centimeter. So we have covered up this part of this numerical, the C part, based on real depth, apparent depth and shift. Next we move on to the, not to the lenses part. Lenses part numerical will be a separate, totally a separate video.